I have been working for many years at the Technical University of Vienna, and as a university you always have to look a little bit ahead of time. And I think the industrial transformation of the technology which we developed at the university into industrial products has been performed by TTTech in a just excellent way. We, personally, well, I am now already retired from the university, but I'm still doing some research, and I think one of the focus of my research is to look at the complexity of systems. And I'm very pleased that Andreas invited me to give a talk about this topic here. Basically, we can distinguish between three subsystems: the operator, the cyberspace, which is normally a distributed computer system, and the physical system, which is the engine or the physical environment that is controlled by the cyber system. And if you look at these two spaces, the physical space and the cyberspace, there are fundamental differences. So we need a computational model where physical time and execution time are properly integrated. And I think this integration of physical progress in the physical environment and computational progress in the computational environment is a key issue in embedded system design.
Please come up stage and give us your presentation. Thank you very much, Dr. Stein.
This talk is not about to convince you that deterministic Ethernet is the most advanced network on the planet and actually in the universe, as you have seen. But it's more intended to give you a kind of a background on why deterministic Ethernet looks as it looks today. What we really want to achieve is the notion of mixed criticality on the node level, where you have hard and software measures in place that guarantee you inference freedom or minimize the interference of the tasks from the different applications on each other. We want to extend this to the network. So it's key that we want to use one single physical network to host the applications in your system, all the applications in your system. We want to minimize the number of different buses that you use in your system. Just to give you an idea is that this was fully compatible to the IEEE standards. So when we talk about Ethernet, we typically refer to two things, to IEEE 802.3, which defines the physical layer and the MAC layers, and we talk about the IEEE 802.1, which defines functionality that's implemented in network switches, for example, in Ethernet switches.
People just at very high level, they say, okay, let's take the average, but we know average is average, but if we care about the phase of execution, and this is something that we do care in real-time system, it very, very depends in even this loop you are doing floating point or integer or vector operation, and it very, very depends on the activity, so you cannot understand the power without understanding the software. And this is something that we see all over again, that doing good power management or understanding the power of the system, you need to do software hardware co-design. You cannot do a good power management just by looking on the hardware or on the software alone. You must understand both sides.
This is a picture from Poland, from KGHM, the third largest copper producer on the globe. They are using conveyors to actually transport goods. They actually have 120 kilometers of these conveyors. For every major, there is 3 of these idlers. In every idler, there are 2 bearings, which are responsible for that idler to actually revolve. If we summarize that, we come to something like 720,000 bearings, which we actually want to monitor. And that's just one company.
You have an ECU for driver assistance, and then you could run script-based test specifications where you emulate the displays and the inputs and the screen model. The whole thing is kind of a virtual prototype simulatable in a computer. Now if you look at the development phases, this is from Hitachi, who are also thinking in this direction. You start with a pure model-based approach where you have abstract models. Fast platforms are available, and since they are in the computer, of course, debugging is much easier. I have a slide that shows this. So that means you can validate your hardware-software integration 1 year before the availability of the real hardware. And this is basically how, if you look at the whole development cycle, a hardware spec, and you have the block design, board design. We have Neon processors, we also have an ARM processor within the EMC2. And then we have all, let's say, hardware components you need to make a typical computer system using a typical MBA HP bus.
I would like to welcome you for this EMC2 conference. This is the second conference that we have, and you're the coordinator, Dr. Weber. And I would like to ask you if you could explain us very shortly what is the essence of the EMC2 project, what is the content of it? Could you summarize that in a few words?
The situation is this. We have advanced in semiconductor technology very quickly. The applications are done too quickly, mostly in consumer applications. Consumer applications are happy with sort of functioning, like 95% functioning, they are happy. If there is a failure, you switch off the device, switch it on again, it will work then. In professional applications and in applications with real-time requirements, such an approach is not possible. So both in applications of mobility like cars, airplanes, space application, but also in applications with large numbers or large amounts of data like you have in manufacturing, in large data centers, you need a much higher level of reliability. And EMC2 wants to close that gap. So this is the main purpose of it. And mixed criticality, dynamic reconfiguration on the software and on the hardware level, and hardware complexity in terms of multi-cores is the essence of this project.
That sounds really very, very interesting. I've been just told that this is a huge number of partners here. Can you give us some of the key figures of the project so we get an impression?
In fact, it is the largest Artemis project ever. It has exactly 100 partners. It has a budget of 80 million, so it is really large. And we believe that essentially the entire European industry and the key players in the academic area are in the project and exchange with one another, which is exactly what we want.
That's really amazing. How do you really deal with all these complex challenges in handling such a huge team? Could you elaborate on this a little bit?
Yes. In fact, I'm not doing all the work. A lot of responsibility is delegated towards the work package leaders, and the work package leaders, of course, have to delegate it down to the partner level. And I think we have a relatively clear cut between the different levels of responsibility, and so even such a large project can be handled. Of course, it requires a lot of dedication from my side, from the side of the project assistant Alfred. But I'm very confident now, after 1.5 years, that we can deal with this complexity. I think it can be done.
Thank you very much, Dr. Weber, and we wish you a lot of success. Thank you very much.
Thank you.